Neuroplasticity is a remarkable characteristic of the brain that allows it to modify, adapt, and reorganize itself throughout an individual's life. This adaptive capacity plays a critical role in learning, memory formation, and recovery from brain injuries. The human brain is an intricate network composed of approximately 100 billion neurons. These neurons communicate with each other via synapses, forming a complex web of neural circuits. Neurotransmitters, the chemical messengers, facilitate this communication. The strength and efficacy of these synaptic connections are not static. They are dynamic and can change over time. This is where neuroplasticity comes into play. Neuroplastic changes are governed by the use it or lose it principle. Synapses that are frequently activated become stronger and more efficient, while those that are seldom used become weaker and may eventually be eliminated. This synaptic pruning is crucial for refining neural networks and optimizing brain function. The brain's plasticity is evident in both its structural and functional aspects. Structural neuroplasticity involves physical changes in the brain, such as the growth of new neurons, known as neurogenesis, as well as the formation of new dendritic spines and the establishment of new synaptic connections. This is particularly evident in the process of forming long-term memories, where repeated stimulation of certain neural pathways leads to the reinforcement and physical growth of these pathways. Functional neuroplasticity refers to the brain's ability to shift functions from a damaged area to undamaged areas. This is most apparent in individuals who have suffered from brain injuries, such as stroke victims, where healthy parts of the brain adapt and compensate for the functions lost due to injury. One intriguing manifestation of neuroplasticity is the phenomenon of phantom limb sensations in amputees. This occurs when the brain continues to receive and interpret sensory signals from nerves that originally served the missing limb. The brain's somatosensory cortex, responsible for processing sensory information, undergoes neuroplastic changes that lead to these phantom sensations. While neuroplasticity is a lifelong process, it is more pronounced during childhood. This enhanced plasticity in children facilitates the formation of complex brain circuits and is integral to the process of learning and acquiring new skills. This is why children can often learn new languages or musical instruments more easily than adults. However, this heightened plasticity also means that negative experiences in childhood, such as trauma, can have profound and long-lasting effects on brain development. Interestingly, neuroplasticity is not just an internal process but can be influenced by external factors. Physical activities, mental exercises, and environmental stimuli can all impact the brain's plasticity. Regular intellectual challenges and learning new skills can promote synaptic growth and strengthen neural networks, enhancing cognitive functions. Neuroplasticity is a fundamental characteristic of the brain, enabling it to adapt, learn, and recover. Understanding and harnessing this remarkable ability of the brain holds immense potential in the fields of education, psychology, and neurorehabilitation, offering hope for treating brain injuries and improving cognitive health across the lifespan.